This conference will now be recorded.
What we say. So, type semiconductor.
Ram, sound is not audible, Ram.
Is it okay, madam? Is it okay?
You speak?
Yeah. So, is it okay now? Is it clear?
Yes, you are clear.
Okay, fine. So, first of all, we'll learn PN junction.
Ram, no sound.
Uh, okay, madam, just a minute.
This conference will now be recorded.
So, good morning, everyone. Today we'll be discussing and learning very important topics from semiconductor chapter. These are the key concept of the diode and transistor will be discussed today. Actually, key concept, if you understand this concept of PN junction and PN junction diodes, what is depletion region or depletion layer, what is barrier potential, how diode can be biased, and what are the diode characteristics, IV characteristics. So those things we will be discussing today. And these are the key concept of solving various problems related to diode or maybe transistors also. So let us learn it very deeply. So first we'll start with p-n junction. Before I say p-n junction, you might be thinking what is p and what is n. So p for p-type semiconductor, p-type semiconductor, semiconductor. And what is p-type semiconductor? We have already learned if you have a germanium crystal or silicon crystal, then if you dope with pentavalent atom like arsenic, antimony, phosphorus, you get you get n-type semiconductor if you dope with pentavalent atom. But if you dope with trivalent impurity atoms like aluminium, boron, etc., if you dope with those trivalent impurity atoms, then you get p-type semiconductor. And in this case, holes, what are holes? Actually, holes means absence of electron, which has effective charge of E positive, equal amount of electronic positive charge. Okay, equivalent electronic positive charge this holes have. Okay, so holes are majority charge carrier, majority charge carrier in p-type semiconductor, charge carriers. Okay, and n for n-type semiconductor, n-type semiconductor. Okay, so n-type semiconductor, and you know, so n-type semiconductor, as I was mentioning, if you dope silicon or germanium with pentavalent atom like arsenic, antimony, phosphorus, then you get n-type semiconductor. Okay, and they have, see, n-type semiconductors having electrons, conduction electrons as majority charge carrier, majority charge carriers. Okay, now p-n junction means what? If you have a p-type semiconductor, okay, and if you have another one n-type semiconductor, suppose, so this is p-type semiconductor, this is n-type semiconductor, then if you have a junction between them, this is the junction, then it is called p-n junction. Generally, a single crystal, it is a single crystal. I'll write the definition. So it is a single crystal of silicon or germanium p-n junction doesn't mean that you have two semiconductors. You have the same semiconductor, a single crystal of silicon or germanium. It is a single crystal of silicon and germanium doped in such a way, doped in such a way such a way that one half portion of it acts as p-type P type, and another half act as another half acts as N type semiconductor. Okay. I'm sorry, my digital pen is giving me some trouble. Conductors. Okay, so this what is semiconductor. Okay, here the term junction means, you know, if you have p-n junction means it is a metallic junction, metallurgical junction. That means at the junction, since you have p and n, here suppose p and this side is n, this is the junction. At this junction you have metallurgical junction. That means at the atomic level there will be differences between this p side and n side, like different this there will be a difference when a charge carrier cross from p to n, so they will feel some difference at this junction. So that is actually metallurgical junction. So p-n junction cannot be made just by placing a p-type semiconductor in close contact with n-type semiconductor. They have discontinuity. Okay, actually two separate semiconductor cannot have a continuous contact at the atomic level. Okay, that's why you cannot do that. You cannot take two semiconductors and then add p and n, then add to get p-n junction. It is not true. Actually you will have either a p type whole semiconductor or a n type whole semiconductor. Then you have to add proper impurity. You have to add proper impurity to get the p-n junction. Suppose initially it was wholly pool p type, and then you add some arsenic here or phosphorus here, then you will see that there will be p region developing here. So at this position there will be a junction between p and n. So that's how the junction is created. It is not like take silver and like copper and then melt them and then like make a junction. It is not like that. Okay, so this is a continuous junction, but still this junction region has a very great physics. We'll see behind it, and this junction is the important part of the diode. So p-n junction is the important part because here there will be a potential, and with that potential, variation of that potential, the conduction of charge, like the flow of current can be controlled. Okay, flow of current can be controlled by just by manipulating this junction region. Okay, we'll now see how p-n junction is formed. How p-n junction is formed, we will see now. So formation of p-n junction. So what I told, first of all, you had only a p type, suppose a whole semiconductor, that is p type. Then you add some parts per million, ppm. What? So here you want n, right? One region n. So you take antimony or phosphorus. Okay, then just add it here somewhere. then you will see the whole region near this will start converting into a P to N region. So the whole region up to here, maybe it may form a N region. Okay, it will form a N region over here. Okay, upon doping. Okay, and see, there is now P region and N region. First of all, this is the thing. So upon doping with antimony or arsenic, you say, you have got P N junction. Now you have, suppose the P, the original semiconductor was highly doped semiconductor, a highly doped semiconductor. Okay, P type semiconductor. That means you have very great hole concentration in the P region. Excuse me. Very great number of hole concentration. And N region also will have a great number of electron concentration. There will be electrons, conduction electrons in the N region, conduction electrons, and here there will be holes. Okay, holes, majority carrier. Okay, holes are generally, I'm sorry, this is electron, conduction electron, and these are holes. All right. So you have majority carriers holes over here, and here electrons. Okay. So when this P and N regions are created, then there will be a junction also created immediately. How it happens? So here you have only holes. Here you have only electron. So with this mechanical barrier, it cannot actually stop the diffusion of the charge carriers. Okay, suppose you have very great concentration or very large concentration of holes over here, and you have very large number of concentration of conduction electron in the N type or N region, then the, because of this concentration gradient, see here there is very less number of N, less N. So there will be a gradient in the concentration level. Okay, concentration, that is called concentration gradient. What is that? That is called concentration gradient. So when you have concentration gradient means you have large number of holes here and minority number of electrons here. Here you will have large number of electrons, you have very small number of holes. Okay, so this is what is the situation now. Now since there is a concentration gradient, because of concentration gradient, because of concentration gradient, because of concentration gradient, what will happen? Diffusion of charge carrier will happen. Diffusion of charge carrier. Okay, diffusion happens. Okay, diffusion of charge carrier will happen. And what is the diffusion? I'll tell you one thing. Whenever there is a concentration gradient, Then there will be diffusion. Diffusion in the sense, in this case, look, I'll clean everything. In this case, you had here N region, here P region. So you have many N here and many, a large number of hole here. Okay. So minority, see, the holes from P, sorry, holes from this, see, you have concentration gradient, so you have large number of holes over here. Then the concentration gradient of the electron is very less over here, so electrons will inject or diffuse in this way. So electron conduction electrons will diffuse. Okay, conduction electrons from N side will be diffused to P side. At the same time, holes from P side will diffuse to N side. Okay, so holes from here goes to N side, and electrons, conduction electron from N side goes to P side. So this is the diffusion. This is called diffusion. Okay, so this is called diffusion. So I will tell you once more. Electrons, see, electrons from N side, they are going to P side, because in the P side there is less concentration of electrons, and at the same time the holes will go from P to N side, P side to N side, because in the N side there is very less concentration gradient of hole here. So holes will come here and accommodate themselves over here. Okay. All right. So when this happens, at the same time you look, when the electrons, they just diffuse to this side, P side, they will leave the positive acceptor ions, positive, sorry, positive donor ions. Okay, positive donor ions, positive donor ions, it will left, it will leave just near the P, sorry, N junction or N side, just at the vicinity of N side. See, since the electrons are getting diffused towards the P side, the positive donor ions will be just residing near the N junction. Okay. Same time, at this similar way, when the holes are diffusing or getting diffused to N side, holes are getting diffused to N side, then near the P junction, holes, sorry, the acceptor ions, negative acceptor ions. Okay, negative acceptor charges or acceptor ions will be accumulated. As you can see from here, positive donor ions are accumulated near the N region, and negative acceptor ions are negative acceptor ions are situating here, just near the P junction. Okay, so these ions are actually acceptor. See, negative is acceptor ions, acceptor, and positive, this is donor ion. So these positive and negative charges are actually immobile. They are heavy, bulky in nature, so immobile. Immobile. Okay, cannot move. So this, since these are just like that sitting at the space, so they are called space charges also. These are called also space charges. Okay, these charges are called space charges, and they actually can understand now that there is p region, n region, and in between there will be space charges, and space charges has positive charge in the near the n side and negative charges near the p side. Okay, and this region is called depletion region because we'll see there will be no free charges at this junction region. You can see that there is no free charge at the junction region. Okay, only the immobile ions are there. So that's why those are called space charges. Space charges cannot move. Okay, but you can see here, interestingly, across this region, this is depletion region. It is called. We'll see why it is called depletion region. At this particular region, one side positive charge carriers, another side negative charge carriers are formed. That means what? That means there will be existing an electric field across the junction, or the potential difference across the junction, since positive charges and negative charges are separated by each other. Sorry, yes, negative charges and positive charges, they are separated here. So there will be a voltage or an electric field produced across the junction. Okay, all right. When this, see, it has electric field direction this way, n to p or n to e. Sorry, n to, let me write n to p. So electric field, there will be electric field that will act in this direction, n to p. But this depletion region, that has very small dimension, some micrometer or millimeter, very tiny. Oh, sorry, this is 10 to the power minus 6 meter. That means micrometer only. So it has very tiny thickness. Okay, if you have electric field, then you can find out potential across this junction also, that is electric field by distance, okay, or thickness of the layer. This, since this thickness is of the order of 10 to the power minus 6 meter, so the electric potential barrier will be a huge amount. E by d is potential difference. So you can see when the diffusion happens, there will be positive space charge region created near the n side and negative space charge region created near the r side, p side. All right, so there will be electric field, and this electric field is called barrier field or barrier potential. We'll learn shortly what is barrier potential. Now you can see, due to diffusion, electrons were going from n to p side, and holes were actually holes were diffusing from p side to n side. So that motion of charge carriers will constitute a current, since the holes positive charges effectively moves towards this. I'm sorry, yes, and electrons, they will move to p side. Okay, therefore by the motion of the charge carriers, there will be a current created, that is called diffusion current, diffusion current, sorry, diffusion current. For the due to the diffusion, there is mobile charge carriers which are diffused. So this is diffusion current which is developed across the junction due to the diffusion. Now, if we apply okay, so what we have got, the diffusion current we have got. So diffusion current has a direction N to P. This is diffusion current. So you can see that I'm sorry, the diffusion current will be in the same direction as hole moves. So P to N. The diffusion current will be in this direction. Diffusion, hole diffusion. So diffusion current. Diffusion current. Now, since there is a depletion region, if there are some electrons nearby, then this N region, because there is a barrier potential now. See, since this positive and negative space charges are here at the junction, so there will be a potential that is given a name V0. This is the potential. That means at the junction, this much potential barrier is there. Okay, so this barrier is here, but somehow at this junction, if there are any electrons come near to this junction, that will be swept away to inside. At the same time, if there are any holes, if you have holes, then holes will be like very fastly they will move to this place. Okay, or the P region. So this is how at at certain time there will be no charge, free charges available. So now one more thing is here that when there is a huge electric field or potential developed across the PN junction, there will be another current also. Like electrons will be pushed from N side to P side, or sorry, P side to N side, and holes will be pushed from N side to P side. Okay, holes will be pushed from N side to P side, and holes will be sorry, electrons will be pushed from the P side to N side. So that is drift, and due to drift of charge carriers, drifting of charge carriers, there will be a current that is called drift current. Okay, so there are two current develops across the junction. One is the diffusion current, another one is the drift current, electronic current. Okay, so this is how the junction will be forming, but at certain time there will be an equilibrium state when the doped current and diffusion drift current and diffusion current become same. Drift current and diffusion current both are drift. Let me write drift. So at the junction when the drift current and drip current and this diffusion currents are same, then equilibrium is established and there is no charge carrier passing from one side to another. Okay, so we have learned what are the things happening while formation of PN junction. There will be space charge region created. Then there will be diffusion current and drip current, and at the equilibrium, at equilibrium, what happens? The I diffusion is equal to I drift. So these two currents will be equal to each other, and then there will be no charges available to flow from one side to another. Okay. So this is about PN junction, how PN junction diode, PN junctions are created. Okay. So, and this region is free of charges. That's why this is called. This region is free of charges. That's why this is called depletion region. So there in the depletion region there is no free charge. That's why the name is called depletion. Depleted. It is said. Now we'll move to. Okay, so one more point I'll discuss over here. So as I said, there will be, since there is electric field, there will be a potential difference also across the junction. As you see, left hand side is P, right hand side is N, and since the space charges are positive near the N side and negative near the P side, there will be potential like potential greater potential in the N side and lower potential in the uh, at the at the side of P type. Okay, so P is at lower barrier potential and highest barrier potential, and C there is, so this is the, suppose this side is P side and this is N side. It is at higher potential P sides and this is at lower potential. Okay. Now this barrier potential, suppose V0. So not all the electrons now pass through this region. Few electrons which has energy E, energy is equal to EV0. Those electrons only will be able to cross this barrier potential. Okay, and take part in the conduction process. So in case of silicon, this barrier potential is almost 0.7 electron volt, and for germanium this is around 0.3 EV. Okay, so this is about barrier potential and depletion region, this part is depletion region, and see width of the, now we'll see this depletion region has a certain width. That width is of the order of micrometer. That's why the potential difference is very large, even though there will be a very small amount of electric field developed across them. Okay, now this depletion region has a thickness, and that thickness depends on, there will be question in your exam on which factors the depletion region or the width of the depletion region depends. So dependence of the junctions so it depends on actually the nature of the semiconductor, then concentration gradient, and also it depends on temperature. Depletion layer thickness depends on temperature. It depends on gradient, concentration gradient, and also it depends on the nature of the semiconductor. Nature of the semiconductor, concentration gradient, and temperature. These three factors are there to control the thickness of the barrier potential or the thickness of the depletion region. Now we'll learn what is, so we have covered already PN junction, then how PN junction forms barrier potential, then PN junction diode. Okay, so PN junction diode we will be learning now. Okay, so what is PN junction diode? We'll learn in the next section. So PN junction diode. See, as I said, PN junction is the basic thing or very fundamental thing for any electronic devices. Actually, PN junction diodes are actually made from this PN junctions only. What is done, there will be metallic contact, as you see at the ends of P and N junction. See, P, this is metallic contact, and this is also metallic contact. Okay, so PN junction diodes are nothing but the PN junctions only, but their sides are actually coated with metallic contact. Now, so since this is created by PN junction, so this junction will act like very, will act as a very important component of this junction diode. Actually, PN junction diode is having a circuit symbol like this. So this region is, this side is P and this side is N. Okay, so this side is N side, this side is P side. Okay, PN junction diode. Diode means it has two terminals, 1 and 2. One terminal is connected to Okay, so there are two terminals, 1 and 2. That's why they are called diode. So this device is called diode because there are two leads for connection, external connection. Okay, so this is p-n junction diode. This is called circuit symbol. This is circuit symbol of p-n junction diode. This is circuit symbol. Okay, so now we'll see we can control this thickness of depletion region. If we control this depletion of region, this thickness of depletion region, then we can actually control the barrier height. You can see that we can change the barrier height. Okay, now we'll see what happens if we connect a positive terminal to this battery and this will be there in the negative. Okay, so this is a type of biasing of diode. Okay, suppose one side is connected to positive terminal of the battery, another side negative terminal of the battery, and look, you have to see whether this is p and this is n. So p side is connected to the battery positive terminal, so this is, and n side is connected with okay. So this kind of biasing when the p side is connected to positive terminal of the battery and n side is connected to negative terminal of the battery, then this kind of biasing is called forward biasing. Forward biasing. So this type of biasing is called forward biasing when positive terminal is connected to the p side and n terminal, like another terminal, but a negative terminal is connected to n. Okay, so let us learn the biasing part. You can see from here when p-n junction diode is connected with battery in such a that the positive, sorry, p type, like the positive terminal of the battery is connected to p type semiconductor and negative terminal goes to n type semiconductor or n side, then this is called forward biasing. And you can see that forward biasing case, the thickness of the depletion region is very less. Okay, so what happens if you apply some positive voltage now here? So there will be actually, see, if the forward bias, at the forward bias, the electrons and holes, majority carriers of the electrons and holes will be there. See, the holes will be going this way and electrons will come in this way because the diode is in reverse bias. So in the beginning, what happens in this case, because of the high concentration of the p and n region, the electrons or holes does not have to go for long distance to recombine. At very small distance itself, the electrons or holes will be recombining in both sides. Okay, so because of that, the thickness is very less over here in the forward bias condition, and also barrier height changes if you apply positive, like if you are biasing a diode, and if the p-n junction diode is forward bias, then your barrier height will decrease. Okay, barrier height will decrease. How it will decrease? If suppose V voltage is applied here, so V minus V0. Okay, so this is how it is actually getting decreased barrier potential height, and hence conductivity will be increasing. On the other hand, in reverse bias case, barrier height increases, and the width of the depletion region, as you see from here, width of the barrier potential will be increasing. Because in this case, minority charge carrier will move from one side to another, and there those minority charge carrier has to move a lot of distance to recombine. Okay, that's how in reverse bias condition, the width of the so this width of the p-n junction in the reverse bias increases. W increases. Okay, in reverse bias, but in forward bias it decreases. You can see that decreases. Okay, as the barrier potential in barrier thickness increases, barrier potential also increases, and that's how they will oppose the motion of the majority charge carriers from each side. That's why this potential is called barrier potential, because it will restrict the spontaneous motion of the electron and holes. Okay, so with this we'll stop it here for today. We'll learn the diode characteristics in the next class, that they will again discuss in detail. So I hope you have understood how reverse bias, in case of reverse bias, what happens? The charge carriers, majority charge carriers will not, like, say you have reverse bias means, this side is negatively charged, so the electrons will, like, holes will come here to here. Okay, and so minority charge carriers will come, because the minority charge carrier has less gradient, like less concentration gradient, then they have to move a large distance to recombine. So that's why the thickness increases, barrier thickness increases. As the barrier thickness increases, the electric potential or barrier also increases. Okay, so with that we'll stop it here for today. next class we will discuss about diode characteristics. Okay, so thank you for your presence. Bye for today.